the naming. And the naming, very straightforward. You always use the whole name of the metal, first part of the non-metal plus IDE. Like that's if you just have what they call a binary compound. So binary is like NaCl, just two elements, okay? Or MgCl2, just two elements. They're called binary because it's two. But if you have those transition metals, remember you got to use the Roman numerals. So only copper, chromium, and iron, those are the only ones that you need those Roman numerals with. And then the other oddball with the ionic was when we talked about the polyatomic. So polyatomic, it's a matter of trying to recognize that NO3 is a nitrate group, that SO4 is the sulfate group. So when you get it in a name or if you get it in the formula, you definitely want to always keep those 7 polyatomic ions that I gave you, keep it close by so that you can kind of compare the name to the name you're given or the formula to the formula of the polyatomic so that you don't say sulfide when it should be sulfate or vice versa. Okay, because remember sulfide would indicate just a sulfur, but sulfate is an SO4 group. So the name does have sort of like, even though they sound a lot alike, having those polyatomics like in a list close by is going to help you a lot in trying to like get more familiar and comfortable with that naming. So covalent are a little bit of a different beast because covalent share electrons. And so there is not just this defined way that two nonmetals can combine. So you may have noticed that in the lab that we did. So we had things like we drew CH4, like we did this in class. So we did CH4. So if we were going to just go about naming this, we would call this carbon hydride. If we were going to name it just like we named the ionic, whole name of the first element, first part of the second element, plus IDE. So that sort of follows that ionic. The challenge, though, is that we can actually have C2H6. Well, if you call that carbon hydride, then it's difficult. Well, which one are you talking about? Okay, and I will tell you that there's actually a C3H8. Carbon, because it shares 4 bonds, can make a lot of different possible combinations. It's not limited like sodium chloride is 1 sodium to 1 chloride because it's their ions and they transfer those electrons. So because there are different possible combinations of nonmetals and hydrogen that exist, this requires that you use what they call a number prefix. The number prefixes are Greek prefixes, and they always go in front of the element that you're describing. So let's look at them. Here are the big ones, okay? So a number prefix, if you have 1, you would call it mono. There is an exception with this one. With mono, you only use mono with the second element. If the first element is a 1, you just use the name of the element, right? So most people are familiar with this. What is this called? CO2 is carbon dioxide. So that's one that you've heard before that's really pretty familiar. So notice in this, you just say carbon. You don't say monocarbon. So if the first element is a 1, you can leave the mono off. And that's because a lot of covalent molecules, the first element's a 1. So that's why they just dropped, like they don't use mono for the first element. But if the second element is a 1, then you do use it. So we said this is carbon dioxide. So what would this be? Capital C, capital O is carbon monoxide. So I still just use carbon for the first element, even though there's only 1 of them. But I need to then put mono for the second element. And notice it's monoxide, not monooxide. So if you have like 2 vowels, they typically drop the vowel off of the number prefix. So that's where it's monoxide instead of monooxide. So then what would you have if you had CO3? That would be carbon trioxide. So the number for the oxygen goes as that Greek prefix in front of the oxide. All right, pen. So if there's 1 as the second element, you use mono. If there's 2, you use di. If there's 3, tri. Now 4 is kind of an odd one. 4 is tetra. And I will tell you that I remember tetra because of the game Tetris. So Tetris was this little game that you used to play it on those little teeny tiny phones way back when. And so it was where the 4 blocks fell and you had to move them and make them fit together. So they're either like a block of 4, like a square, or a straight line of 4, or an L of 4. So they would just like drop from the sky and you'd have to like line them up to make them match. Well, that's Tetris. And it got its name because the word tetra is a Greek term that means 4. Once we go past 4, though, then they start to fit what I think of as geometrical shapes. So a pentagon has how many sides? 5. And a hexagon has 6. Heptagon has 7. An octagon has 8. Then the nona, that's an A. Nona is 9. And then deca, can't write it over there. Deca would be 10. You don't really see 8, 9, and 10 too much, but just know that they do match like what a normal geometric shape would actually be. Bless you. Now, what if the first element is not just a 1? So what happens if I have N2O? I have to define the number of nitrogens. It's not just the second element you have to put a number prefix in front of. I need to put a number prefix in front of the first element as well. But I still keep the whole name of the first element, first part of the second element plus IDE. So in that respect, it's a lot like how you named plain ionic. But I've got to add a number prefix, and it might sound strange, but the more you practice it, the more normal it starts to feel. So if I have 2 nitrogens, that would be called dinitrogen. I still keep the whole name of the first element, but I put di in front because there's 2 of them, and then that oxygen becomes monoxide because there's 1 of them, and it's the second element. I've got to include the term mono. So what would this be? N3O6. Trinitrogen. Hex oxide. So like I said, if there's 2 vowels, and that'd be fine if you put hexaoxide, I wouldn't mark it wrong, but the mastering might. Okay, so just know if you have 2 vowels, so if your number prefix and your element name, if there's 2 vowels, drop the vowel off of the number prefix. So you would drop like the A off of hexa, or you would drop the A off of tetra, or the A off of penta. You don't drop the tri, though. You wouldn't drop the di. You don't drop an I, but if there's an A, it would. Okay? So trinitrogen or hexoxide just means 3 nitrogens and 6 oxygens based on that name. So you've got your sheet, that handout sheet. Try these ones. Very good. All right, trinitrogen dioxide. What did you put? N3O2. Okay. So remember that the number that's considered the subscript, that is telling you how many. So this just means 3 nitrogens, 2 oxygens. The number after the element always tells you how many, and it always goes as a subscript. So I did notice in lab, some people were like switching the superscript and subscript numbers or mixing them up. If it's written like this, that means 2 nitrogens, 3 nitrogens, 2 oxygens. What about tetrasulfur pentachloride? Yep. 5. So that just means 4 sulfurs, 5 chlorines. Dicarbon hexahydride. H6. Hydride is hydrogen. Okay, so remember that nonmetals and hydrogen are what make your covalent molecules. So you probably not heard hydride because you're not going to see that with those ionic ones. So that one's kind of a weird one that probably the first time that you've heard that one. So just remember hydride, that would be a hydrogen. So then, going back and doing the opposite, CF4 would be carbon, tetrafluoride. And remember, fluoride, it's UOR, otherwise it's flour. SO, though, would be sulfur. So is it sulfur oxide? What's missing? Sulfur monoxide. Did everybody get that one? Right? So I don't have to put mono for the sulfur because it's the first element. So if there's only one, that's not a problem. Second element, if there's only one, you got to put mono. Okay? It's the only time you have to use the mono. And then P2I4. Di. My pen's going crazy. Di. And this is the one that's the fun one to spell. The challenge. Diphosphorus. Tetra. Tetraiodide. And it's really tetraiodide, but I wouldn't care if you left the A in or took it out, because that's a lot of vowels all stuck in there. Okay, so now the next part. The next part is what I call the mashup. Because this is going to get you to, one, identify is the name or the formula, is it ionic or covalent? So while you were working on those, I sort of wrote like little like cheat for you at the top and the bottom. Remember that covalent, all nonmetals and hydrogen. So all you've really got to do is look at the name or the formula and then look at the periodic table. If you don't have a periodic table, you may want to run up here and grab one because there is no zigzag line on that one. So it does make it a challenge. I always put the periodic tables out. So remember, if it's nonmetals, then everything is going to be to the right of the zigzag line or hydrogen. Then I know it's covalent because that's nonmetals and hydrogen. If the first element is to the left of the zigzag line, then that's a metal and I know that it's ionic. So the first thing I would do is go through each one. Just look at each name, look at each formula, find where the first element is on the periodic table, and from that, define, is it ionic or covalent? Then go back and do the naming according to which type it is, because ionic, you're going to name without number prefixes. Covalent, you need to use the number prefixes. With ionic, you have those two weird transition metals need Roman numerals, and polyatomics are that group of ions. So I'll give you a minute. So these are on that handout, that sheet. The ionic versus covalent column, the last column first. So iron 3 sulfide, is it ionic or covalent? Ionic. Because iron is a metal. You should see it to the left of the zigzag line. CaNO3 is ionic, because calcium is to the left of the zigzag line. S4O2 is covalent, because sulfur, S, is over to the right side. Then potassium nitride, ionic. Then PBr3, covalent. Pentanitrogen trihydride, covalent. Cu3P, ionic. And then the last one, ammonium phosphate. It's actually ionic. And when you think about it, you're like, well, wait a minute. If you look, ammonium is a what? It's one of the polyatomic ions. So if it's a polyatomic ion, then you know it's going to be an ionic compound because you're going to have two charges that are there. So that is actually, the ammonium is actually the oddball because it starts with the nitrogen, which is a nonmetal, but because it's a polyatomic ion, that would be an ionic compound. All right. So now that I know whether they're ionic or covalent, now I can go about naming them. So the first one, iron 3 sulfide. So iron 3, what does that mean? With a charge of +3, right? So that Roman numeral tells me it's a +3 charge. Then sulfide. So what is sulfide? It's just S because it's sulfide. And the charge on a sulfur is 8 minus group 6, so it'd be a -2, right? So remember, if you get iron, chromium, copper, the Roman numeral is the charge. I would do this first. Just go ahead and write down the symbol, assign the charge. Now I have to do the swap. So the number on the iron tells me how many sulfur. The number on the sulfur tells me how many iron. So the formula is Fe2S3. Okay, next one is ionic. It's CaNO3 parentheses 2. So what's its name? Calcium nitrate. So NO3, you have to recognize that that is the nitrate ion. And remember that you just use its name. Okay, so for the polyatomics, you just use their name when giving the name from the formula. What about S4O2? Tetra, sulfur. It's a sulfur. There's 4 of them. And then dioxide. Which means 4 sulfurs, 2 oxygens. Now going down to the next one. So potassium nitrate. Which first, K with a what charge? +1, because it's over in group 1. And then nitrite is an N with a -3. So just write down the symbol, assign the charge. Remember that the metal, it's the group number is its positive charge. The non-metal is 8 minus the group number. It's always a negative charge. And so then when you swap them, what does it end up being? K3N. So the 3 on the nitrogen tells me how many potassium. The 1 on the potassium tells me I only have 1 nitrogen. So those numbers swap to tell me the formula. What about PBr3? Phosphorus tribromide. Pentanitrogen trihydride is, N5H3. Pentanitrogen, 5 nitrogens, trihydride, 3 hydrogens. All right, now Cu3P. So what's Cu? So Cu is copper. And then what's P? Phosphorus. But instead of just naming it this way, what do I have to make sure I add? The Roman numeral. Does anybody know what the charge is? No, it's not a 3. That's the number of copper. Remember, the Roman numeral tells you the charge. So I've got to figure out the charge. So on this, so I'll just put it up here so you can see it big, right? So if you look at phosphorus, phosphorus is in group 5, so its charge will be a -3. Do you see that those match? The -3 and the 3 copper? See that diagonally they match? So that means diagonally the other 2 will match. So since this is a 1, this is a +1. Okay, just like what we did with the swapping for iron and sulfur for potassium and nitrogen, you assign those charges and swap them to figure out the formula. You kind of do this reverse. So you work out, okay, I know what the phosphorus is because it's not going to change. I know the phosphorus is a -3. Because the phosphorus is a -3 and I have 3 coppers, then I know that the other 2 are going to match as well. So that one's a 1, so this is a +1. That tells me I have to put a Roman numeral 1 in between the copper and the phosphide. And it should be phosphide, sorry. Not phosphorus. Copper 1 phosphide. Whole name of the metal, first part of the non-metal plus IDE. But with iron, copper, and chromium, I got to add that Roman numeral. The Roman numeral is the charge. You might want to put a note, not the number of the iron, copper, of chromium, because that's like one of those common mistakes right along with saying that P is potassium. All right, last one. So last one is ammonium phosphate. So what's the ammonium ion? NH4, and its charge is plus. Okay, that's a terrible N. Handwriting today is awful. All right, so NH4. So notice what this looks like. So it's an 1 nitrogen, 4 hydrogens. So that's the NH. The 4 is down low, and it has a +1 charge. Okay, not a +4 charge, because it looked like some people were getting those kind of numbers and charges flipped, or they were trying to combine them in lab. So this is a NH4 molecule with a +1 charge. What's the phosphate? PO4 with a -3. -3, 3 negative, doesn't matter. So notice this one means there's 1 phosphorus, 4 oxygen, and it has a -3 charge. So the number down low tells you how many. The number up above is telling me the charge. Okay, so they don't combine together. They're like telling you two different things about the molecule. So then when I go to find this answer, what do I have to do? Just swap them. So the charge swapped tells me the formula. Which one of those do I put in parentheses? The ammonium. So the NH4 has to have parentheses. Notice I keep NH4. I don't put the 4 outside. The 4 stays with the hydrogen because that's still 1 nitrogen and 4 hydrogen. But outside that parentheses, I put the 3. What about the phosphorus? Do I need parentheses? No, because there's only 1 of them. So then I just write PO4. So if I have only 1 polyatomic, you don't need to use parentheses. But if I have more than 1, by doing that swap, put parentheses around the polyatomic. Don't change its formula. Just put the number outside, which gives the formula of how many of those. Okay? So NH4, notice it doesn't change when I go to find the formula. PO4 doesn't change. I might change the total number of them by using parentheses, but you don't want to change the formula of the polyatomics. So hopefully that helps a little bit in the naming. There is ionic naming, ionic bond formation. There's some dynamic study modules that you have due Sunday night, but they're all going to help you go through this. There's also the covalent. So there's a covalent molecules dynamic study module that you should go ahead and do, because that's also going to help you to start practicing this naming. All right, so a couple more things. So and what I will do is I will actually put the answers to these. So if you've printed out your PowerPoints, I will put the answers in for these couple of slides, and you can go back and check. Remember that I saved this PowerPoint. It's posted in Moodle as the marked up PowerPoint. So it's in your exam 2 module. It will say chapter 3. Well, it says Chem 130-01, chapter 3, marked up PowerPoint. That just means it's the PowerPoint with my notes. Okay, so if you want more practice, if you're like, I think I got it, but I'm not 100% sure, then you can go through and do these, and I'll put the answers for these in mine and then post it. So you'll have more that you can use to practice. So now we're getting into a little bit more theory. So when we talk about these molecules, we like to draw them in that Lewis structure, and they look really flat. Okay, but electrons arrange themselves so that shared pairs of electrons get as far apart from each other as possible. So I've got, and I just went ahead and built them. So I have one. So if you've been in lab, then I know that you've seen these, so you can kind of look at them and pass them along. But if you haven't been in lab, then you haven't had the opportunity to look at like the models and be able to like visibly see the 3-dimensional image. But the one that's going around is CH4, carbon with 4 single bonds. And when you look at it, you can kind of then see how it looks like that bottom right image, that 3-dimensional shape. The electrons, remember that this is 2 electrons. This is 2 electrons, this is 2 electrons, this is 2 electrons. Electrons are negatively charged. So electrons are going to try to get as far apart as possible as they can from each other. That is what forms this shape. They called this shape the tetrahedral. So a carbon with 4 single bonds will always have a tetrahedral shape. So it doesn't matter if I had a carbon with 4 hydrogens, or if I had a carbon with 4 carbons connected to it, or if I have a carbon with an oxygen and 3 hydrogens connected. If there's a carbon with 4 single bonds, it'll always have that tetrahedral shape. So they said this is explained by what they call the VSEPR. VSEPR is VSEPR. So the VSEPR theory just says valence electrons, shared pairs of electrons, want to get as far apart from each other as possible because they're negatively charged. And you know that like charges repel each other. So they push each other apart, and that's what creates this shape. they'd sometimes draw this, and you may have to draw something like this, in mastering. So the little wedge and dash is just to try and show like the three-dimensional structure, but on a flat piece of paper. So if you see a straight line, like a Lewis structure line, like this first one, if you see these two H's, that would indicate like those would be flat on the paper. So they would be like flat on the projector board. But the wedge would indicate that this hydrogen would actually be sticking out. So the wedge would always show like something sticking forward out of the plane of your paper or out of the plane of the projector surface. And then this wedge shows behind. So the wedge sticks forward, the dash, I call it the dash, dash, dash. So the little dash looking one, this is meant to show that it would actually be pointing back behind this plane. So that's another way that they'll sometimes try to show you like three-dimensional structures without having a three-dimensional structure. The wedge, always remember that's the black solid line, looks like it sticks forward. The dash, dash, dash is going to be like sticking back behind your piece of paper. Just a different way of looking at it. So they said, okay, well, yeah, so CH4 looks like a tetrahedral, but how do you recognize a tetrahedral shape? It's always a carbon with 4 single bonds, so it really doesn't matter what it's connected to. If carbon has 4 single bonds, it is always going to have that tetrahedral shape. So they said, well, we're going to use, in this Vesper formation, we'll use a terminology called the ABN designation. So A is always the central atom. So remember when you draw a covalent molecule, the central atom is the one you put down first, the one that always needed the most bonds. And if you look at the model we're sending around, it's the one that looks like it's in the center. Okay, so it looks like it's in the center of them. B is how many groups are bonded. So B is bonded groups. And it doesn't matter if it's a single bond, a double bond, or a triple bond, that counts as one bonded group. Because it's just one atom connected. Either it's connected by a single bond, a double bond, or a triple, but it's still just considered a single group connected. Now N, carbon doesn't have this, but some atoms like oxygen and nitrogen, they have non-bonding electrons. So remember that when you draw like the valence shell number for nitrogen, nitrogen's in group 5. And so those 2 electrons at the top, those are called non-bonding electrons. They belong to the nitrogen. They do not participate in a bond. The other 3 do, but not that pair at the top. So those are the non-bonding pairs. So non-bonding electron pairs, so it's not a single electron, it's always going to be a pair. So if we have 1, like nitrogen, 1 pair, N would be a 1. With oxygen, how many non-bonding pairs does oxygen have? It's always going to have 2. Okay, so in the one that I just drew, the top group is a non-bonding pair, the left side is a non-bonding pair. So it's only the right and the bottom electrons that are going to form a covalent bond to make their stable 8. That is why oxygen always forms 2 bonds, because it's got those 4 electrons that don't participate. Those are non-bonding. So that oxygen typically has N2. Nitrogen, however, is just going to be an N. It only has 1 pair of non-bonding electrons. So the easiest thing to look at is first with carbon. Because carbon can have 4 different kinds of bonds, if carbon has 4 single bonds, doesn't matter what it's connected to, it'll always be tetrahedral. So what's the ABN for that? If carbon is A, how many groups will it have connected to it? So that's AB4. And AB4 always has that tetrahedral shape. So what about the second one? How many groups are connected to the carbon in the second one? 3. Okay, so in that one, I have formaldehyde, which is that CH2O. And if you hold it up, you can kind of see that it looks like a triangle. Okay, it's got 3 points to it. That's that double bond to the oxygen. So it'd be like this one. There's, you can see that double bond. The other thing though, is because they get exactly 120 degrees apart, they lay real flat. So you see if I hold it, can you tell that it's flat? Like I could actually put it like flat up on the board. It wouldn't stick forward, it wouldn't stick back, it's actually flat. And that's where this name comes from. So trigonal is like 3 because it looks like a 3-sided figure, like a triangle. So trigonal, but planar, the term planar means flat. So trigonal planar is the term that they use for this. And what's this ABN? This would be AB3 because the carbon has 3 groups attached. And so again, it doesn't really matter what the groups are. I'm really just looking at like how many groups are connected to that carbon. So anytime you have an AB3 group, or if you have carbon with a double bond and 2 single bonds, an AB3 will always have a trigonal planar arrangement. Last one. So the last one is the carbon dioxide. So you'll see these are all the 5 that we actually used as examples for us. So this one here. So if carbon has 2 oxygens, those oxygens get as far apart from each other as possible because remember that these bonds are electrons and they repel each other. So the bonds that are in between are kind of stuck where they are, but they want to get as far apart as possible from the other bonds around the central atom. So that's as far apart as they can get. It's really considered like 180 degrees on opposite sides. And so when you look at this molecule, it looks like a straight line, right? So it looks like this straight line. That is the linear shape.
Question for you.
Mm-hmm.
If you have C2,
Mm-hmm. If you have 2 carbons, you mean? Okay.
and they're bonded together, does it create 4 different bonds?
Well, that's all chapter 4. So chapter 4 is all about organic molecules, which are the molecules of carbon. So like I could have carbon, like I could have lots of carbons. But if all of these carbons have single bonds, they're all going to be what shape? They're all going to be tetrahedral. So if you see this one carbon has a group of 4, second carbon group of 4, third carbon group of 4, they will actually all have a tetrahedral shape. Okay, so I could look at individual carbons versus like the entire, and then it kind of changes the entire shape of the molecule. So it's not really a flat shape. It ends up looking like a little zigzag kind of a pattern to it. But yeah, we'll talk about why, like how you end up with those kinds of shapes. But this is just looking at like a specific atom. Okay, and I say, okay, well, if I'm looking at this atom that's in the molecule, as long as it has more than 1 bond, it doesn't really matter if it has 1 bond, it has no shape. It's just stuck onto something. But if it has more than 1 bond, then it's going to have some kind of shape to it. So linear would be called AB what? 2. So it's AB2. So AB2 would always have the linear shape. So in lab, we did just a couple of different ones. So we had some different molecules. We just swapped out hydrogens, and they were still having these basic shapes if carbon was involved. The other ones are these non-bonding pairs. So these are the last 2. So for this top one, this is NH3. So notice with nitrogen, nitrogen's different than carbon because it has 1 pair of non-bonding electrons. This 1 pair of non-bonding electrons actually takes up space. And what it does is it pushes those hydrogens so that they can't get exactly far apart. They end up getting pushed. And if you look at this one, can you see how that nitrogen's a little bit higher than the hydrogens? That is because the non-bonding electrons up here actually kind of like push those hydrogens down. Non-bonding electrons have a stronger repulsion, have more force than bonding electrons do. Because the bonding electrons go like this. Bonding electrons go back and forth, back and forth. They don't just stay with the nitrogen, they kind of go back and forth. So those non-bonding electrons, they belong to that nitrogen. So they actually take up more room around that nitrogen and create a stronger repulsion effect. So I always think like it pushes them. this creates almost like a cloud. Non-bonding electrons take up more space. They take up more space around their atom. And repel bonding pairs with the greater force. And that's why nitrogen doesn't just spread its 3 bonds out like into a triangle. That's why you end up with this slight elevated appearance. This creates the pyramidal shape. So pyramidal, how many groups are connected? It's A. How many B? 3. So it's AB3. How many non-bonding pairs does that central atom have? It has 1. And that's why it's different than trigonal planar. Trigonal planar has 3 bonded groups, just like pyramidal does, but pyramidal has that non-bonding pair that changes the shape slightly. Last one. Last one is what oxygen likes to do. So oxygen has 6 valence electrons. So that means that this non-bonding pair and this non-bonding pair have their big space. They actually push those hydrogens or the other bonded pairs, they push them even more than nitrogen does. So like see the bond angle? The bond angle with NH3 is 107 degrees. The bond angle with water, with H2O, is only 104. So it actually pushes those even more because of the non-bonding pairs that are there. So there's the last one if you want to pass those so they can do a comparison. So if I hold this the little model up, here's what water looks like. Remember that means those non-bonding electrons are here, and see how much of a curve you end up with. So those hydrogens can't get on opposite sides like CO2. So remember with CO2, the oxygens are on opposite sides. But here, those hydrogens get pushed and create this shape, which is called bent. And it's because of the non-bonding electrons. So if oxygen has 2 single bonds, what's its B? It's AB2 because it's always got 2 groups connected to it. This one's the bent. It's got AB2, but then how many non-bonding pairs? 2. This is why this is different than carbon dioxide. Carbon dioxide, those oxygens can get opposite of each other because carbon has no non-bonding electrons. So the opposite, you get that linear arrangement, even though carbon just has 2 groups connected. Here, oxygen has 2 groups connected, but because of the non-bonding pairs, it's going to create more repulsion and create the bent shape. So this chart, you do not have to learn bond angles. Do not worry about that, okay? But for this, you should know, like that AB4, that's a carbon with 4 single bonds, and it's always tetrahedral. An example for this one would be this, CH4. Second one is what happens with nitrogen. If nitrogen has 3 single bonds, like NH3, it'll always have this non-bonding electron group, and it's going to create a pyramidal shape. Third one is what happens when oxygen has 2 single bonds. You'll always end up with this little bit of a bend to it. Water, best example. And remember, these are all the ones that we just drew as covalent molecules. Trigonal planar, this is CH2O. This is the formaldehyde molecule where carbon has a double bond and 2 single bonds. And so in this case, it ends up allowing those 3 groups to get exactly equal distance apart, making a nice little triangle. So that's the trigonal planar. And then the last one, our example is carbon dioxide, where you have a carbon in the middle, 2 groups connected, no non-bonding electrons, and that's going to create your linear shape. Oh, you mean like why is it sometimes CH4 and sometimes there's something else? It's almost like like historical. It's almost like that's the way that they started naming, and covalent is the one that's the odd one. Sometimes like phosphorus will be out front, sometimes phosphorus is the second one. Now with ionic, it's always metals and nonmetals, so they're always arranged that way. The positive ions are always written first, the negative are always written second. But for covalent molecules, it just depends. It just depends. And in fact, like there's different, you'll see the same one sometimes written different ways. Okay. And again, that's a chapter 4 thing, because we're going to talk about more organic molecules, talking about organic molecules, carbon containing molecules. That's really the whole focus of chapter 4. So of all of this, this is kind of like the piece, the bits of information that you want to take with you. Okay, that you may want to end up putting on your note card, like add this to the list, being able to recognize that AB4 is tetrahedral, okay, that AB2N2 is bent, that AB3 is a trigonal planar. And then these are good examples because we've actually drawn these. We've actually looked at these. You've already done these. These are the ones that the molecules I sent around. These are just good general examples. Like these will be the ones that I ask you. So if I ask you, what is the shape of a water molecule? You should be able to say, water molecule, I know that's AB2N2, and I know that that's going to look bent, okay? I'd give you the formula, I'd say H2O. I wouldn't just ask you water. I'd give you NH3, I'd give you CH2O, as like if I asked you what the shape was. But these are all ones that we've done. So just kind of make sure that you go back over their shape, the way that we drew them in class last time, to help you go through it. So there's more. We're not doing those. So here's like your example. So Jessica, so notice that if you have bigger molecules, you can actually define the shape of every atom that's in the interior of a molecule. I can't really tell the shape of a hydrogen because this is all hydrogen does. That's not really a shape. It has to have at least 2 bonds to be able to have a shape. And so I could talk about the shape of the first carbon, second carbon, and even the oxygen. But I don't really talk about the shape of the hydrogens because they're the groups that get connected to. All right, so why do you have to know the shapes? We want to know the shapes because the shapes are going to help you to visualize polarity and this understanding of this characteristic that covalent molecules have. Not all covalent molecules share their electrons equally. And this is because of this term. The term is called electronegativity, and it's really the attraction of an atom for its electrons and any electrons that it shares. So if I have H2, just 2 hydrogens, remember that that would just be a hydrogen here, change the color, hydrogen here. Those 2 dots, like realistically spend 50% of the time with one hydrogen, 50% of the time with the other. So I like to put the dots like right in between. So it's a very equal sharing because they're the exact same atom, okay? So they're the same element, so they're going to share them equally. That's a covalent bond, right? So when you put the little dash, you would say that this is a neutral molecule because the electrons are evenly distributed between those 2. Neutral molecules are also called nonpolar. So nonpolar molecules share their electrons equally, but not all elements do that. And the 4 that are really electronegative, they are very attracted to their electrons, is nitrogen, oxygen, fluorine, and chlorine. And if you look at your periodic table, those are the ones that are the smallest nonmetals, closest to the noble gases. So they're the ones that are up in this corner. So that's really why I drew them that way, because you see NO, F, and Cl. They're the smallest elements that have the closest to 8. This chart, you don't have to memorize any electronegative numbers. We're not going to do any calculating of electronegative differences or anything like that. But looking at this, they gave a scale. They said, okay, well, if we look at all the atoms on the periodic table, and we could say a electronegative scale of 0 to 4. 0 is the lowest, 4 is the highest. which ones have the lowest electronegativity? When you look at this. What do you think? Cesium. That's not one you had to know. Cesium, barium, rubidium, those ones are very, very low, but these are all metals, right? Those are the first two columns. So metals have a very low electronegativity, but then look, as you go across from left to right, what do you see happen to this number? It increases, and as you go from the bottom of a column up, it also increases. Even in the very first column, lithium is a 1, cesium is a 0.7. So as we go up and as we go to the right, the attraction of an atom for its electrons increases. So I was telling them in class, in lab, I said, okay, so if you think of sodium, which has this electronegativity of only 0.9, you know that it has 1 electron in its outer shell because it's in group 1. So you can think of it as it like holds that 1 electron way out. It's very loosely held. In fact, it wants anything to come by and take it because then the next level down is full and it's stable, like a noble gas. But if I was going to look at fluorine, on the other hand, see that it has an electronegativity of 4. So if I was going to draw its Lewis dots, I would put them as close to that fluorine as possible. It pulls them in very tight. And so if I put these two together, this is really why ionic bonds form. Because the sodium has such a low electronegativity, it just gives its electron to the fluorine. Here. And the fluorine sucks it right in. And then that makes fluorine have 8 and it's stable. And the sodium, by losing its 1, the next level in is full and it's stable. So this is big difference in electronegativity is the reason why ionic transfer of electrons occurs. So you already know that, right? You already know sodium becomes positive, fluorine becomes negative because it's a metal and a non-metal, so you get that transfer that happens. But what's the difference? What if carbon and fluorine form a bond? And you've done that, right? So we've seen molecules like that. So if we have like a carbon with the 2 fluorines and the 2 hydrogens, we did this one in lab. Okay, so those bright orange balls that you did. So in this, we just drew them like little dashes. But in fact, the electrons are going to end up, the ones that are between the carbon and the fluorine, the dash line, those are a pair of electrons. Where are they really going to sit? Are they going to sit right in between the carbon and the fluorine? They're going to get sucked over closer to the fluorine. They're still shared. It's not a transfer, but they are going to spend more time with the fluorine than they're going to spend with the carbon. So if I redraw that one, and I'll just put the dots. So the ones between the carbon and the hydrogen, they're actually really shared quite evenly. But the ones that are between the fluorine, and I'll put my fluorine right here, it's going to be kind of more like this. So this fluorine, that's an F. Are going to spend more time around the fluorine, whereas the carbon and the hydrogen, they're actually going to be more evenly distributed. Because if you look at hydrogen is 2.1, carbon is 2.5. They're pretty close. So if electronegativities are close, they're going to do more equal sharing. But notice then that these electrons get pulled this way, the electrons get pulled that way. So the electrons get pulled towards the fluorine. So do you see that one side of this molecule becomes more electron dense? So we really have more electrons over here, less electrons over here. Because of that, that side close to the fluorines becomes slightly negative. It doesn't become negatively charged. So it's not ionic, it's still sharing. So it's still covalent, but it's an unequal sharing, which creates a slight charge. So you would say this side is now slightly negative. That's going to create this side where the hydrogens are as being slightly positive. They like to use a funny little symbol. The symbol looks like this. It looks almost like an 8. It's a Greek delta symbol. I know my symbols never look like the book, but this one would be a little delta symbol with the negative. So that's saying there's a slight positive and negative arrangement in this molecule. This is a polar molecule. No, ionic bonds are ionic. Okay, so we have ionic bonds and then we have covalent. And then within covalent, you can have polar and nonpolar. Okay, so it does affect how they interact, and that's kind of the next thing. And so here's sort of the way to recognize you have a polar molecule if it's small and you have one nitrogen, oxygen, fluorine, or chlorine. That's really the thing to remember is on the periodic table, nitrogen, oxygen, fluorine, and chlorine, they are not going to share their electrons equally, and that's going to create a polar molecule. So small molecules, and only one nitrogen, oxygen, fluorine, or chlorine going to be polar. If there's more than one, that's when you need to know the shape, because you want to know, are the two electronegatives on opposite sides? Do they balance the molecule? Or are they kind of like CH2F2? Are they both on one side? So knowing the shape of the molecule, it's the whole reason to talk about geometry, is just because the shape of the molecule does come into play. So like this one that I just drew, where I said if you have this, you look at this molecule and go, oh, there's two fluorines. Those two fluorines are on one side because it's that tetrahedral. That side's going to become negative, the other side positive. This is polar. So there I have two. But then what about this? So CO2, you go, oh, there's oxygens. Well, oxygen's a nitrogen, oxygen, fluorine, or chlorine. But you see that they're on opposite sides? This balances them. So here, there's two electronegatives. But they balance each other, and the whole molecule ends up being a neutral molecule. So this side becomes more negative, this side becomes more negative, but they balance each other out. So this is nonpolar. Whereas this one is polar. This side becomes negative, that side becomes positive. So thinking about the shape, and it's the reason we do those 5 three-dimensional shapes, because you want in your head to see, if you see a carbon with 4 single bonds, you want to remember it's tetrahedral. So even if you saw a carbon drawn like this, you would want to recognize that's not balanced because it's the tetrahedral shape. Because I've got the bonds coming off at 4 points, I can take and move or flip my molecule around and make it look like that. I can put the fluorines on one side. But with CO2, I cannot. Carbon dioxide, because of those double bonds, they're on opposite sides, whether they're like this or like that. They're always on opposite sides. That is why they balance each other. Okay? So here it shows, and this is like, I wish I could make this, I needed to make this a whole lot bigger. Occasionally, nope, it's not going to let me zoom. Occasionally it lets me zoom. So that one, CH2, the two hydrogens, they share their bonds very equally. So notice that the little dots look like they're like right between the two hydrogens. Then if you look at the one that's next to it, which is HCl, having a covalent bond, notice how the electrons look like they're closer to the green chlorine, not as close to that hydrogen. So that is why this side becomes slightly positive. This side becomes more negative. That creates this polar molecule. But if I looked at HCl, I would say, oh, there's one chlorine. It's polar. Okay? So if I look at NH3, polar or non-polar? Polar, because there's only one nitrogen. So remember, if there's only one, always polar. Okay? So like carbon monoxide. Polar, one oxygen. Nitrogen, oxygen, fluorine, or chlorine. Okay, so if you saw like CH3Cl, polar, one chlorine. Okay, if there's only one nitrogen, oxygen, fluorine, or chlorine, I know that it's going to be polar because these are small molecules. The electrons are going to get pulled towards the electronegative, creating that slight charge difference. But if you see something like this, are there any nitrogen, oxygen, fluorine, or chlorine? No, nonpolar. So one we did in class was this. pH 3. Polar or non-polar? Non-polar, because there's no nitrogen, oxygen, fluorine, or chlorine. Okay, and that's the majority of them. That's really what you do, is you just look at the formula, or you look at the name, and if you see that there's only one nitrogen, oxygen, fluorine, or chlorine, then you know it's going to be a polar molecule. If you see more than that, then you really have to kind of think about the shapes. And we'll stick to most of the simpler ones, but both of these ones, those would be non-polar. So what's the significance of this? So things that are polar like to interact with things that are polar. So the most polar molecule is one that is the most abundant molecule in the body, so water. So water being polar, because it only has one oxygen, it's a nice polar molecule, then it'll interact and mix with other polar molecules. So like ammonia, NH3 has one nitrogen, I know it's polar. So those two, you can take ammonia and water, you can dilute ammonia, so it's not quite so smelly if you're using it for cleaning. Other things you can think of, sugar. Sugar has oxygens, and those oxygens being electronegative increases polarity. So sugar, you take sugar, put it in water, stir it up, completely disappears, it dissolves because it's able to interact. Vinegar, another one. You can dilute vinegar, so you can have like vinegar from the jar, but you could dilute it for cleaning. It also mixes. Things that are polar mix with things that are polar. The other thing that polar likes to mix with is polar likes to mix with salts because they have a similar charge. So if I take water and I add some sodium chloride, I know that's ionic, but sodium chloride can mix with water because they still have that charge characteristic. So this has made water like a great universal solvent because water mixes with lots of polar things, lots of your vitamins, your electrolytes. Remember the salts, the ions we talked about in the last class? Water can mix with those. A lot of your nutrients like amino acids and sugars, water can mix with those. And so we can have this solution of lots of different bits and parts that completely stay dissolved because they have similar, slightly charged or charged characteristics. But non-polar. So remember in non-polar, remember it means there's no nitrogen, oxygen, fluorine, or chlorine. If there are those, they have to be balanced in the molecule. Okay, so there's either none of the electronegatives, or if there are, the electronegatives create a balance in the molecule. So something like chlorine, Cl2. So remember Cl2, you're like, oh, but chlorine's an electronegative. Yes, but chlorine, when it exists as chlorine gas, has to share its electrons equally because they both have the same pull. They just get really close together because they're like mine, no mine, right? But they're still, those electrons end up right in the middle. So chlorine's a non-polar molecule. Gasoline, grease, oils, butter, bacon grease, lard, meat drippings, all of those things, all those greasy kind of things, most of your lotions, anything that has like a greasy residue, those are all non-polar. So non-polar typically have lots of carbon and hydrogen, very little, if any, oxygen, nitrogen, fluorine, or chlorine. So these are ones that you should think of when you think of those non-polar stuff. The waxes, butter. I can mix these. Things that are non-polar are very neutral, right? So non-polar molecules are extremely neutral. They don't have any slight chargedness or ions. They're very neutral. Their electrons are very evenly distributed, but they'll mix together. The next time that you fry something, the next time you put oil in your pan, even if you're going to saute, I want you to take and put some salt in and look at the salt crystals. What do you think the salt crystals do when you put them in oil? Do they dissolve? No, because they're actually opposites. Salt is sodium chloride, charged ions. They don't like things that are neutral. So you'll see them, they'll drop right to the bottom and they'll just sit there. They will not dissolve because there's no water. So your cooking oils, When they say to salt something, you don't typically salt the oil. You wait till you've added the food and you salt the food, because the food is going to have water in it, but the oil is not going to have water. So it's like pointless. It'll just drop right to the bottom of the oil and not interact with it. So things that are polar, things that are ionic, they mix. Things that are polar mix. As long as they have even a little bit of a charge, they can mix with ionic. But things that are non-polar, they don't mix with ionic. Things that are non-polar, they don't mix with anything that's polar. So that's why I sort of drew this line down the center. So non-polar does not, will not interact, mix with polar or ionic. And so again, another kind of fun thing you can do, if you have any Italian dressing or even vinegar and oil, and you like shake it up and watch, it almost looks like the oil gets pushed out of the way. It like gets pushed out of the water, vinegar, seasoning area, because they want to interact, and that oil is like neutral, so it just gets like shoved out of the way. So you'll see these droplets get pushed towards the top, and it's really because the polar and ionic components all want to mix, and they're not going to want to mix with that non-polar. We will talk more about solutions, homogeneous versus heterogeneous, and how you can end up with polar versus non-polar and making them mix later, chapter 8. We wanted to introduce it. Oh, and I guess I about to quit. I thought I might get to moles and molecules. This is the last topic in this chapter. It's not the last topic in the e-text, but it's my last topic because I like to cover all of that and do this one last. This is the only math on this test. Okay? And it's just about, how do you count molecules? How do you know what you're measuring out when you're like mixing things and measuring a gram of this or a half a pound of that? How do you know how much you have? So we're going to talk about moles and molecules next time. And then we'll start chapter 4. So do make sure you get your pre-lecture for chapter 4 done for Tuesday, because we will start pre-lecture. We'll start chapter 4 on Tuesday.